Hello physics students, this is Dr. Brenzi, and this is the video I promised to talk about problems 4 and 5 on Formative 5.2. First of all, I want to thank Alex Flores and Alex Hopkins for sticking around after school and working personally through this with me. It took a long time. And through that process, it was pretty obvious to me that I really shouldn't have put this on a formative. So I want to apologize to all of you just like I apologize to them. But it is a useful process to go through because you're going to be dealing with problems that don't have numbers in them on the AP exam. So it was in that spirit that I attempted to put a problem on there that I probably should not have done or should have modified so that it was more time manageable. But let's go through this anyway. And don't worry about when you do the corrections, you're going to get full credit for this anyway. So let's go through this process. All right, so the way I like to think of this problem is in 3 phases here. So first of all, I like to think of phase 1 as like the mass M swinging down. And then the phase 2 is when the collision happens. And then phase 3 is when the blob, that's the 2 masses stuck together, they swing up to a different height. So I want to think of those 3 things as 3 different phases, and you'll see as we're thinking about this why I split it up in 3 phases, because different things are conserved during each of these phases. All right, so in phase 1, we just have the mass M swinging down from a height h. And when it gets down to its lowest height, all of that potential energy that it had at the left initially becomes kinetic energy. And since gravity is acting on the object, that's an external force, so we can't say that momentum is conserved. But gravity is a conservative force, so we can say that total energy is conserved. So that's what we're going to use in phase 1 is energy conservation. So at the start, the total amount of energy is all potential, so mgh. And at the finish, the total mechanical energy is all kinetic, so it's 1/2 mv naught squared. Well, energy is conserved, so I can set those two equal to one another. And then it's pretty trivial process to solve for V naught, and you'll get V naught equals root 2gh. Now, we didn't need that in any of the problems per se. Well, it's not an answer to any of the problems, any parts of the problems, but we need that in order to go on to phase 2. So phase 2 is the actual collision itself. So in phase 2, we have a before and an after collision. So before the collision, we have the little m going at a speed v naught, which we just figured out, and the 5m mass is going at 0 velocity, so it's stationary. And then after the collision, these two stick together, and they move at a velocity v1. Oops, I'm getting ahead of myself here, or at least my writing is. Now in this case, we don't have gravity acting for a very long amount of time here. You can think of this as immediately before the collision and immediately after the collision. So even though we have an external force, we say that it interacts for such a little time during this process that we can say that it doesn't have an effect and therefore momentum is conserved. So in this process, we can find the total momentum before and the total momentum after. And I'm again getting ahead of myself. So this is the total momentum before the collision, immediately before. This is the total momentum after the collision. I set those two equal to one another, and I solve for V1. And I get V naught divided by 6, but we figured out what V naught is in the video or the slide before. That's just root 2gh. So the velocity of this blob right after the collision is root 2gh divided by 6. And that's the answer to part A for problem number 4. Part B asks us what height does this blob go to after the collision. So that is phase 3. Phase 3 is this big blob moving at this velocity, which we just figured out. And it is going to swing up until it reaches a height h1. Now, in this process, gravity is obviously changing this blob's velocity, so we can't say that momentum is conserved in this process, but again, it's a conservative force, so that we can say total mechanical energy is conserved. So now I'm going to go back to mechanical energy conservation. This is the exact opposite process of phase 1. So now we start with kinetic energy, and we finish with potential energy. The total mechanical energy is conserved, so I can set these two equal to one another. And when I do a little bit of algebra, I get H1 equals V1 squared divided by 2G. But I know what V1 squared is. I figured that out before from the collision. And when you square this V1 squared, you get 2GH over 36. And you can do a little bit of canceling, and so you get H1 is equal to the original height divided by 36. So this blob actually swings to a height that is very small compared to the original height of the little mass m. All right, so that's part B for number 4. And then if we go to part C, it's asking how much energy was lost in this collision. So what we want to do is we want to take the energy that it finished off with, which is the potential energy of the blob when it's at its maximum height. So it's 6 mgh1. Plug in this expression for h1, which we just figured out in the last slide. And we do a little simplifying, and it turns out that the energy at the finish is 1/6 mgh. Now, the total energy we had at the very start of the process was mgh. So we take the difference of that to figure out the loss of energy, and it turns out that we lost 5/6 of our original energy. That's quite a bit. So that was part C for problem number 4. Okay, problem number 5 is definitely, it's the same process, similar process, but it's definitely worse than this one. I might be able to convince myself that I could put number 4 on there. I probably shouldn't have put number 5 on there. But it's the same process. Phase 1, we have the little m swinging down. Phase 2, we have the collision. And phase 3, we're going to have both balls swinging to a maximum height, but they're going to be swinging to different maximum heights since they're not connected anymore. All right, so phase 1 is the same as for problem number 4. Nothing changed there. So we know that when that mass m swings down, just before it hits the bigger mass, it's going to have a velocity equal to root 2gh. If you need to review how to do that, go back to the beginning of the video. Phase 2, here's where the collision happens. So before the collision, we have just little m moving, 5m is at rest, and then after the collision, each of these is moving at a different velocity. Now, you might debate the direction of my arrows here. You might say, hey, wait a minute, doesn't this one bounce off the other direction? Well, let's be naive here, and let's actually assume that they both bounce and go the same direction. They could do that, that's possible. But let's be naive, put them both in the same direction, and then if we end up getting a negative value for V1, then we know we have to switch the direction of this arrow. Okay, so during this collision, we know that momentum is conserved. So the total amount of momentum before the collision was just mv naught. The total amount of momentum after the collision is mv1 plus 5mv2. And because momentum is conserved, we can set these equal to one another. So I get mv naught equals mv1 plus 5mv2. It looks like I have mass on both sides of that equation in each term, so I can divide those out. And this is what I get. I'm putting this in square bracket or a square box because we're going to come back to that later. We're going to end up having to set up a system of equations, and this is the first equation of our system. Okay, so that is momentum conservation, but the problem for problem number 5 told us that this collision is elastic, which means that not only is momentum conserved, but kinetic energy is also conserved. So now let's handle kinetic energy conservation. So let's redraw the diagram. And now, because the collision is elastic, we are going to be dealing with kinetic energy conservation. So the total kinetic energy before the collision is going to be 1/2 mv naught squared. And the total kinetic energy after the collision is going to equal 1/2 mv1 squared plus 1/2 times 5m times v2 squared. And since kinetic energy is conserved, I can set these two values equal to one another. So I'll just put an equal sign right there. I notice right away that each of my terms on both sides of the equation has a 1/2 m in common. So I'm going to go ahead and divide that out immediately. And what I'm left with is v naught squared equals v1 squared plus 5v2 squared. So that's the second equation that's going to go into my system of equations here. All right, so now let's put those two equations on one page and figure out how to solve the system. So we have v naught equals v1 plus 5v2. That's what we got from momentum conservation. And then from kinetic energy conservation, we ended up with this equation right here. Now, this is probably not anything like you have seen before for a system of equations. What do we have to do? Well, I noticed that one of these is v naught, one of them is v naught squared. So why not take this one, square both sides, and then substitute out for this? So I'm going to take this equation and square both sides of it. And let's square both sides. And when I do that, I get v naught squared, and then I have to multiply that binomial out. And boy, it looks like I made a worse mess than before. But now let's take this equation and let's plug it in. Actually, no, what I want to do, I'm going to take this equation and I'm going to replace v naught squared with this, and then I'm going to plug in this down here. So I'm going to have v1 squared plus 5v2 squared equals that same term on the right hand side of the equation. Now it definitely seems like I've been making a mess of this, but the mess is going to now start to clear up. I notice that I have a v1 squared on both sides of the equation, so those are going to subtract out. And then I am going to get everything onto one side of the equation. And when I do, I get 0 equals 10 v1 v2 plus 20 v2 squared. Now let's factor out a common factor of v2. And I have two things that are being multiplied together and their product is 0. Well, that means that one of these two factors has to equal 0. So I actually have two possible solutions. Either this factor is 0, which means v2 is equal to 0. Oops, I'm getting ahead of myself. Right, and that's kind of like the boring case. Or we can say, and the reason that's the boring case is because that is exactly the case that we had before the collision where the big mass was at rest. Or we have 10v1 plus 20v2 equals 0. And when I actually solve that for v1, I get v1 equals negative 2 times v2. Now, let's do a little bit of a sanity check before I go and plug this into another equation. So remember that v1 is actually v2. I drew v2 first for some reason. Let me draw v1. So v1 is the mass of little m after the collision, and v2 is the mass of, or the velocity of big M, or 5m after the collision. So what this equation, this result is telling me is that this v1 is equal to 2 times v2, so it's going twice as fast, but since there's a negative sign, it's twice as fast in the opposite direction. Does that seem reasonable? Well, I guess maybe I would have expected a bigger result, but it kind of does make sense that it's going in the opposite direction. Now, if I had a result that said that this has to be a bigger speed, then I know that something went wrong with my math and I would go back over it. But I think it's somewhat reasonable, so I'm going to stick with it. Okay, but now what do I do with this? What do I do with this equation? Well, I can take it and plug v1 into one of my original equations up here, either one of them. It would definitely be easier to plug into this equation. So let's plug v1 into that equation, or actually replace v1. So we're going to replace this with negative 2v2. So let me make a little space for myself, and let's bring down this equation. And let's replace v1 with negative 2v2. So I do that substitution, and I'm going to get v naught equals 3v2. And I'm going to solve for v2 because that's what I'm interested in. And remember back in phase 1 that v naught is equal to root 2gh. So now I get v2 equals 1/3 times root 2gh. Okay, so I found the velocity of the big mass after the collision. The velocity of the little mass after the collision, I can just use this equation to figure it out. So I just need to take this little guy and multiply it times negative 2. And so that turns out to be negative 2/3 times root 2gh. So that would be your answer for part A, and that is definitely not something I should have put on a formative. I am really sorry. But let's do it for educational sake. Let's finish off problem 5 here. So part B is asking for how high each of the balls goes. So let's go on to phase 3. We have the big mass going to the right at 1/3 times root 2gh, and it's going to come up to a height h3. We have v2, the velocity of the little mass, and that's going negative 2/3 times root 2gh after the collision, and it's going to swing up to a height h2. We have to figure out what h2 and h3 are. Well, this is a case where we go back to energy conservation because we have gravity acting on both of these masses during the swing. So gravity being a conservative force, we go back to energy conservation. And let's conserve energy for this little mass here. So we write mgh2 is equal to 1/2 mv2 squared. And the m's cancel out. I replace v2 squared with negative 2/3 root 2gh, all of that squared. And when you square a fraction, you square the numerator, square the denominator. So I'm getting 1/2 times 4/9 times 2gh. It looks like the 2 and the 1/2 will divide out. The g's on both sides will cancel out. And it turns out that I get h2 is equal to 4/9 times h. So this ball, little m, will come back to 4/9 of its original height. Seems somewhat reasonable. Let's figure out how high this mass will go to. So let's do the same thing. Don't forget that you have 5m for the mass. But it turns out that the first thing I see is that there's a factor of 5m on both sides, so it's going to divide out right away. So if you made the mistake of putting m in there, you've made a lucky mistake. Okay, and I do the same process, and it's going to turn out that H3 is 1/9 of the original height that this little ball was at. And that makes sense, since this is a big mass, it's it's probably not going to move up very far. Okay, so those are the heights of the two balls. That's part B. Then part C. We're almost there. Is energy conserved throughout this entire process? Now, let's think about where we absolutely began at the very beginning and where we ended at the absolute end. So at the very beginning, we had little m at a height of mgh. So that was how much energy we started off with. We ended up with two different masses at two different heights, but the total energy is just the potential energy of the two added together. So if I use my result from part B and plug in 4/9 h for H2, I see that the energy stored in this ball after everything's done is 4/9 mgh. I'm going to plug in 1/9 h for H3, like we found out in the previous slide, and I'm going to get a total potential energy of 5/9 mgh. So if I add up all of the potential energy between these two, after the collision, I get 4/9 mgh plus 5/9 mgh. Well, that's 9/9. And that's just going to be mgh. And that matches the energy that I started off with. So it is true that energy was conserved throughout this entire process. And we just show that we didn't lose any energy. Let's put it that way. All right. So, again, long problem. I shouldn't have put it on a formative, I'm sorry. But it was, I think, an educational process nonetheless. Good luck on the summative tomorrow. And I definitely told Alex and Alex this, and I'll tell you this now if you're watching this video. If you get a problem like this tomorrow on the summative, it's going to have numbers, and it's not going to be this crazy. I will guarantee it. Because, well, I'll just have to say I guarantee it. Okay? Have a good evening. Good luck studying, and I'll see you tomorrow. Bye.